we'll get started. Okay, so first thing that I wanted to communicate to students in lecture, so either the students who are here now or students who might be watching this later today, I talked a little bit about this on Piazza. We released the midterm exam grade yesterday, and I know that that's often a stressful experience, no matter how you did on it, and that especially this semester, it's just one potentially stressful thing among a set of horrifically stressful current events. So I just wanted to reassure everyone, a single midterm grade in this class is not a deal breaker. If you're looking to improve exam-wise for the final, I'm happy to chat with you, can offer some ideas based on how you did on this exam. But also remember, your recitation participation grade is worth more than the midterm. Your design project deliverables collectively are worth more than both exams combined. We give you a lot of feedback on participation on the design project deliverables. As a result, most students do well on both of those as long as they're responding to the feedback. But the staff is totally happy to talk to any of you about any part of your grade in this class, to offer tips to improve if you feel that you need to, even if it's just to offer reassurance that you're on the right track. And certainly if you feel like kind of all of the events in the world are making it difficult for you to do well in 033, reach out to us. We'll do our best to help, right? So let's talk about atomicity, all right? Will I release the grade distribution? We don't release grade distributions, okay? We don't grade you in comparison to your peers. We don't grade on any sort of a curve. If you all earn A's, you will all get A's. I found that in the past when we've released grade distributions, it's actually increased anxiety and distress, especially for students who maybe didn't do so well on the midterm, but are going to go on to do just fine in the class. So no, we don't release those distributions, right? So atomicity, where did we end up last week, right? This is where we ended, not last week, on Monday. What a long week it has been for all of us, all right? So we ended up talking about this abstraction of transactions, right? And transactions are gonna provide us with both atomicity and isolation, right? Atomicity means we're gonna have this guarantee that a transaction either executes entirely or not at all, no matter where a failure occurs. And then isolation tells us something about whether certain actions are visible when two transactions are running concurrently. In lecture, we're gonna aim to get a particularly kind of strict level of isolation, right? And so why is this good? Why are we working towards this? Well, if we have atomicity, it means that we don't have to worry about our system being in some intermediate state on a failure, right? The action happens or it doesn't happen halfway. Isolation is gonna let us reason about concurrency, which to be honest is gonna be useful even if things aren't failing, right? So our job in lecture is to think about how would a system implement these two abstractions? Like how would we make transactions possible? We're not gonna spend time in lecture thinking about like, well, here's some code, what should the transactions be, right? Because the answer to that question is different. It depends on what the application is doing, right? What should be a transaction in a bank is different from what should be a transaction in a system that's like Amazon or something like that, right? So we're trying to implement these things. Where are we? We talked a lot about atomicity on Monday, and we do have this working for one user and one file via shadow copies, right? The problem is that they don't perform very well, right? In particular, that we have to overwrite an entire file even for just tiny little changes, right? And we haven't talked about really how to generalize them, in part because the performance is so bad. We're gonna go with a different technique. Isolation, we really don't have this yet, right? You should have a sense that locks are gonna come into play here, and they are, but we sort of left locks in the operating system section as being kind of unsatisfying, right? We don't like global reasoning. They're sort of difficult to reason about, right? So we're going to eventually address that. But today we're still thinking about atomicity, right? And in particular, we're going to try to provide atomicity without hindering performance, all right? The mechanism that we're going to use to do this is known as logging, all right? So logging is going to provide us with much better performance at the cost of some added complexity. right? So let's see how this is going to work, right? Here is the example that we're gonna base most of today's lecture off of. All right, and so I'll just talk about the syntax really quick before we introduce a log. It's in a weird place on the slides because I'm gonna add to it. All right, so I have 3 transactions here, T1, T2, and T3. They're gonna run they're not running in parallel, they're going one right after another. All right, and you can see we're doing some writes and some reads. All right, so for instance, this first line, writing 100 to A, okay, that's effectively just saying A equals 100. The next line, B equals 50. All right, and then transaction 1 commits. All right, that means that these writes have been committed. We'll talk specifically about how the system deals with that. All right, so then we go into transaction 2, which looks a little bit more complicated because there are these reads alongside the writes. All right, but what is happening here, for instance, in this first line? All right, we're reading in the value of A, subtracting 20 from it, writing that back to A. Same thing for this read of B, right? Take the current value of B, add 20, write that back. All right, and then we have this transaction number 3. And you can see the transaction 3 on the slide here. It gets started, right? It's doing A equals A plus 30. All right, and as you can imagine, things are gonna crash. All right, so this is, these set of transactions, they're not doing anything super exciting. They're adding some values to these variables A and B, but they're set up in such a way to illustrate a couple of points as we go through this lecture, right? So here's the basic idea. The basic idea is for us to keep a log of all of these changes, right? And whether transactions are committing, right? So I'm gonna set this up for you. It's not going to perform well initially. So a lot of this lecture is about how do we get logging to perform well, right? Not just about how do we get atomicity. So to do this, all right, let's think about what happens. Suppose there's a crash here, all right? Well, what could be problematic here? What are we trying to deal with? We've written this value to A, right? It's equal to 110, but T3 didn't commit, right? That transaction didn't go all the way through. Somehow our system is going to need a way to revert to the previously committed value of A, right? Which happens to be 80. All right, so we're going to use a log to do this. Let's just see, here's what the log is going to look like. I'll talk about writing to it, reading to it, all right? What's going on here? So whenever we begin a transaction, we're going to allocate a new transaction ID. So those are the things like T1, T2, T3. This is so we can distinguish one transaction from another, which isn't terribly relevant here because our transactions are just proceeding in sequence. But eventually we're going to live in a world where transactions could be run in parallel, all right? So we want that unique identifier, and you assume it's unique, okay? It's going to be unique. And you can see as we go along, there's kind of 2 different types of records here, right? We'll start, you can see these update records. All right, so whenever we want to write a value, we write one of these update records, right? So for instance, this first write that sets A equal to 100. You can see that here in the log, the first record in the log, right? You'll assume A and B are initialized at 0. So you can see we have the old value of A and the new value of A, right? We're going to use the old value of these variables in a particular way. This will become clear as we go through this example. All right, same thing with these writes. The write of B, right? This next line of this transaction, here it is in the log. All right, and then when a transaction commits, as T1 does here, right? We write a commit record, right? So we're updating things, we're writing commit records. Initially, what seems good about this, right? Why is this going in the right direction? All right, well, notice that unlike with shadow copies, for every transaction, every update, we're only writing the values that change, right? So when I update A, I don't have to say anything in this log about B, right? Just write an update for A, right? So don't have to copy over every single piece of data in the file. And in fact, I'm illustrating this on the top here as appending to a log. That is what would be happening on the disk as well, right? These are appends, so they're particularly fast writes, right? But now does this log do what we want it to do? Right? Does it actually give us atomicity? This is sort of, what it's going to look like. How's it going to give us atomicity? So the way that we're going to understand this is by talking about how we read this log. All right, so let's go through that. How would we use the log to read a value? All right, so here's how I'm gonna present this to you. We're not actually worried about a crash yet. Imagine though we've gotten through the first transaction, right? And now we're starting to execute this first line of T2. All right, the reason I'm using this line is because it's the first place we're doing a read of the value. All right, so at this point, the log only has these 3 entries in it. All right, we haven't done the write in T2 yet, but we've written all of transaction 1. So let's try to read that value of A. How is this going to work? So here's what the read code is going to look like. This is very pseudocodey. I'll go through the code at a high level, and then we'll actually do this example. All right, the way this is going to work is that this code reads backwards through the log. So it starts at the end and goes backwards. And it's looking for whether a transaction has committed. If it has, it's going to keep track of that. Right? And when it comes upon an update record, if the update is from a transaction that committed and it's the variable we're interested in, then we've found what we need. All right. So let's see how this works to read this last value of A. Right. We're going to keep track of this commits data structure. It's just a list of transaction IDs, or a set would be fine too. Right. So we're at this last entry in the log because we're scanning backwards. Right. So this is a commit entry, right? We found a commit record. So we're going to add this transaction to our list of committed transactions. Right? This is what databases mean when they say a write-ahead log, although it's going to get a little bit more complicated, and I will use the term write-ahead log in 10-ish minutes. All right? So we're at this last record here. We found it. It's a committed transaction. Okay, so we'll move on to the next one. Right? This is an update record. Right? So, okay, the type is update. This transaction did commit, but this isn't the variable we're interested in. This is an update of B. We're interested in A. All right, so this doesn't help us here, but that's fine. We will go to the next record. Right? Similarly, this is an update. This transaction is committed. It's in this list. And hey, this is the variable that we wanted. Right? So we're going to return that new value, which here would be 100. Right? So here's our reading process. And notice that, for this log is very short at this point. We've actually reached the beginning of the log. So in some sense, of course we stop here. But if there had been previous updates prior to this, we're not scrolling back through them. We found the latest committed update of A. We can return it. We can go on with our lives. All right. Now, we're not quite done with this because there's one feature missing. All right. We haven't talked about crashes yet. We're going to come to that in a second. Briefly, imagine that this write has gone through, and I'm going to take us into an alternate universe where T2 is just slightly different than it was before, right? Because I want to illustrate one additional point. All right, so we have this code here now for T2, right? And this is effectively doing A equals A minus 20, and then A equals A minus 30. Right? And yeah, you can look at this and say, like, why not just one line that does A equals A minus 50? Sure. But, this is a simple example to illustrate a particular point. Because of the way we imagine these systems working, it makes sense that T2 should be able to read its own writes, even though it hasn't fully committed yet. Right? That is a behavior that we might want. But unfortunately, it's not a behavior that we would get from the code as it is, right? When T2 goes to execute this second read of A, read is looking for the last committed value, right? That's the value that T1 committed. It's not the value that T2 just wrote. So we're just going to adjust the code a little bit, right? And we're going to let us read our own updates, right? So a transaction gets to read its own updates, even if they haven't committed yet. And again, this is just the nature of how we would write software to solve these problems. So that's the only small update we're going to make to read. But otherwise, here's read, right? Scan the log backwards, find either the last update that this transaction wrote to this variable or the last committed update before that, right? So what does this mean, right? Let's go back to our previous example, right? Original example. We've gotten through all of these steps. So we have the whole log up here. And then there is a crash, right? So the system crashes, it comes back up, right? The log is on disk, the log is stable, right? To recover from this crash, right? Do I have to do anything, right? The concern here is that, we wrote this update to the log, but T3 didn't commit. This is fine. We don't have to do anything to repair this log. The log is good. It's an uncommitted update. It's not going to be read by anything. Even if you imagine like, well, wait, what if T3 like restarted and couldn't it read its own update? It would get a different transaction ID, right? T3 failed, we're onto a different ID now, right? This is great. This means our recovery process is, instantaneous. And what you can notice from this is it means that writing that commit record is the commit point, right? That's the point at which a transaction is committed. And about commit points. The commit points themselves need to be atomic, right? So one approach from last time, and I think is totally believable in this setup, writing that commit record is a very small amount of data. You can imagine that write fitting within a single sector, right? So it is feasible for writing that commit record to be atomic, just from the size of the write. There are alternative approaches though, if for some reason that record needs to be larger than a single sector. Other approaches would involve, say, putting checksums on the records, which would then alert you if the commit record was only half written, right? So there are lots of ways to handle this. The easiest for us to think about is to just assume that the write of the commit record is in a single sector. All right, so now let's think, how well does this perform? All right, we're gonna care about reading, about writing, and about recovery. So I have a quick poll, and I'm just curious, of these operations, right? Writing a log entry, reading the value of a variable, recovering from a failure, which of these do you think is going to be the slowest, right? Anonymous, I'm not going to share the results. Just think about it in the example that we have so far. And when I say recovering from the failure, I don't necessarily mean that the entire time that the machine is down. I mean, once it comes back up, how quick is it for us to repair the log? All right, so I'll give this a little bit of time. There should get some like Jeopardy-like poll music. Okay, so we have about 80% reporting. I think that's a good number. So let's think about this, right? Let's think about writes. Writes are actually, writes are gonna be relatively okay for us, right? We're appending to a log. It's true we have to do a write to a disk, but that's sort of what we have to do if we want reliability. They're sequential, right? They're not random. We're only writing small updates. So writes are pretty okay. Reads, on the other hand, can get very bad, right? Imagine if this log entry is 1 million records long, and the value of the variable you're trying to read was written on the very first record. You will scan backwards through the entire log, right? Now, we shouldn't let logs get that long. We'll come to that at the end of lecture. Reads here can be quite slow, right? This is the problem that we want to address. Recovery, on the other hand, recovery is okay. We don't have to repair the log or any sort of data storage on recovery, right? Because remember, like if you look at this log, in this example, this is the concerning record. Oh, my pencil has gone away. All right, that last update is the concern here. right? That update is okay. It won't be read. It wasn't committed. In a way, it's as if it didn't exist. So what we want to do now is we want to improve performance of our reads. All right, so here is how we are going to improve performance of our reads. You all know some techniques to make reads in a computer faster, right? One of the techniques that you know is, well, okay, put a piece of data that I'm reading a lot, somewhere where I can get to it quickly, right? Like your instinct might be to say, oh, a cache. A cache sounds exciting. That's a great idea. We're going to go with something that's just a little bit different from a cache at this stage. All right, so here's what we're going to add. We're going to add what we call in this context cell storage. All right, the log is just as it was before. It's authoritative. It's going to provide us with atomicity. I'll go through the example again. The goal of cell storage is to provide us with fast reads. All right, but it is super, super important to understand, and we're going to go through the example, super important to understand that this cell storage, it is on a disk. It's not an in-memory cache. It's on a disk. If the machine crashes and comes back up, whatever you wrote to cell storage last will still be there. All right. So how do we use cell storage? Let's not have anything crash yet. All right. How are we gonna do reads? How are we gonna do writes now that we have sort of this, secondary piece of information? All right. Well, when we read, we're no longer gonna scan through the log. Right. We're gonna read straight from cell storage. Right. There is a cell that tells me the value of A. I'm just gonna read from there. I don't have to scan. This means now, whenever I'm writing to values, I've got to keep that cell storage up to date. All right. So when I write an update, it's got to go to the log, right? The log is authoritative. Everything needs to get to the log. And then we're also going to write to cell storage, right? And if you're concerned about a crash in between these two lines, that's a great thing to be concerned about. We'll talk about that in just a second. All right, but to start you with some words, the words that we associate with this, we log an update when it's written to the log, and we install an update when it's written to cell storage, right? So you'll often hear people talking about logging and installing, right? So now, some questions, right? Now, if there's a crash, we might have some work to do, right? For instance, how do we recover cell storage from this authoritative log after a crash, right? And again, you should look at this and be a little bit hesitant about the fact that I've taken a write, and kind of added a second step, right? So let's talk about recovery because it'll answer that other question, right? So we're gonna look at the same example, right? We're gonna have a crash here, and let's think about how we would recover, right? Because let's think about first what's wrong here, right? If the system comes back online after this crash, the log is fine, but cell storage is incorrect, right? Cell storage reflects a write of A that was uncommitted, okay? We would like that value, that write of A equals 110 to be undone, right? It should go back to being equal to 80. So we can do this. We can write a recovery function that does this. All right, so here's how it's gonna look. Again, I'm gonna explain it to you and then I will step you through the log. It's not dissimilar from what a read looked like before. We're gonna scan backwards. We're gonna keep track of what transactions committed, but this time, all right, this time, if they haven't committed, we wanna undo any writes, all right? So let's see how that's done. Give me one moment of pause while I plug in this pencil to recharge it in hopes that we might be able to use the pencil later. We'll see how that goes. Okay, so let's see how this works. All right, so again, we're keeping track of which transactions were committed. Keep them in this list. All right, we're gonna start with T3. And this is the most exciting part. We start off with a bang. All right, looking at this transaction, it's not a commit record. It is an update record, right? And in fact, it's an update record that wasn't committed. right? T3 is not, we have not found that T3 was committed, right? Which, it wasn't. So we're gonna undo, right? We're gonna write the old value of A, right, which is 80. Now, we're all sitting here and you can look at this example. You're already kind of intimately familiar with the example at this point in the lecture. You can see that this is correct, right? We have the right values of A and B. These are the values that we want in the end. But let's keep going. Let's just make sure we understand like why it would not roll back even further. All right, so we'll keep going, right? Our next record, it's a commit. This is great. We're gonna keep it as part of our list, right? Now we come across 2 updates, right? So they're update records, but this transaction has been committed. There's nothing to undo here, right? So we're not going to take any action on this update or on this update. Now we come to an additional commit record. It's great. We're going to add it to our set, our list, right? And same thing with T2, right? Both of these updates were committed. There's nothing to undo here, right? So notice, right? If we log an update and install it, right? And then, the system crashes, we needed to undo that installed update, right? So what we did here is we scanned the log, determined, what actions didn't commit and undid them, right? We scan backwards, right? Because we needed to undo from like newest to oldest, right? And we need to figure out the outcome of the actions before we decide whether to undo. All right. Notice also, we talk a lot about crashes sort of during the transactions themselves, but what if you crashed during this recovery process? That is also a consideration, right? In this particular example, and this is something that we want for all of our systems, we can keep recovering over and over and over again. This process will be fine. We'll get the same results. All right. And from this example, you can start to see, hopefully, why the ordering of logging and installing matters, right? Why we log before we install, right? Because it's very true that we could crash in between those two lines, right? So imagine they were switched. Imagine that we did the installing and we did the cell right before the log, right? If we crash in the middle, we've written something to the cell, but it's not in the log. We would have no record of it. We, in fact, wouldn't even know necessarily that it would exist to undo it, right? This is, in some ways, this is the golden rule of logging. Always log the update before you install it. The log is meant to be authoritative and intact. We use the log to repair the cell storage. Cell storage is just here as a performance gain, right? So this protocol, this is known as write-ahead logging, right? We're logging before we're installing, right? So let's check in again, right? All of these, the logging that we had before worked fine, right? We went down this road though to try to optimize the performance of reads. So let's think now, how is this performing, right? Reading, writing, and recovering. How are things going, right? Well, reads have improved, right? We do a lookup in cell storage, right? Imagine it's kind of like a dictionary stored on a disk. That's great. We've really improved the process of reading. We don't have to scan backwards to the log every time, right? Writing, it got a little bit worse, right? Now we have to write to the log, which again, that's a given. We have to write to the log. We have to write somewhere permanent to make this work out. And then we also have to write to cell storage, right? So now we write twice, right? Still, it's a small write typically, but it's twice, right? And now our recovery process though, this has gotten, this has gotten a lot longer, right? We have to scan the entire log because we have to repair cell storage now. And, that's going to take longer and longer as the log goes, right? So, let's see if we can address this, all right? We're going to be able to address both issues in different ways, all right? And so the first thing we're going to deal with is writes, all right? How can we make writes a little bit faster? All right, so we're going to add a third thing into the system. We have a log, we have cell storage, which we're excited about to optimize reads. And now we are going to add a cache. And we're using the word cache here because now this is in memory, just the way you expect a cache to be. All right, it's going to cause us some problems, right? We've added another thing that we have to try to keep consistent. So we're going to come to that. But let's imagine, performance-wise, what's going on here? How are we going to read? How are we going to write? Let's not worry about things failing yet. All right, well, reading. If the variable's in the cache, we're going to read right from the cache. All right, so if we got a cache hit, reads are even speedier now. We don't have to read from a disk. If we're trying to read a variable that's not in the cache, right, we're going to pull it in from cell storage. We're going to put it in the cache. We might have to evict something else. So this is operating very much in the way that you would expect a cache to work. It's a limited amount of memory. You can't keep every record in the cache necessarily. We can on cell storage. That's a disk. That's fine. All right, so we'll need an eviction policy. We don't have to worry about the details of how that works here. I just want you to understand that it's a cache, right? It's in memory, it's volatile, it's small, it's fast. All right, now what about writing? Okay, so writing, there's a couple of things that are gonna have to go on. We're still gonna log first. We have to write to the log. If we're not writing updates to the log, the whole system falls apart around us, right? And then we're gonna push that update to the cache, right? Which sort of leaves the question of well, how does anything ever get to cell storage, right? Well, okay, occasionally we're gonna flush the cache. Everything that's been written to the cache, we're gonna move it to cell storage, right? And of course, as part of our eviction process, I might be pushing some data to cell storage there as well, all right? And I said that flushing is called occasionally, and that's gonna matter. We'll see an example, all right? But so I'm reading directly from the cache, I'm writing to the log first, then I'm writing to the cache. I'm pushing the cache to cell storage every once in a while. This is how the system is working. So if nothing is crashing, I'm doing a lot of interactions with the cache, right? A lot of my reads and writes are gonna be very, very fast. This is great, right? But now, what happens when things fail? This is our recovery process from before. How is this gonna work out now, right? So for me to take you through this example one final time, you need a little bit more information, right? Because we've added this cache, we need to understand well, okay, what does the cache look like? What does cell storage look like? So for this example, the recover code will come back, don't worry. Suppose that we flushed the cache after T1 committed, right? But haven't flushed it since then, right? So here's what that means for you. It means that T1's updates, those are in cell storage. Those are on disk. They will persist through a crash. But none of T2's updates have made it. T3's update hasn't made it to cell storage, right? Which is in some ways good, right? Because it's not a committed update. This is what cell storage and the cache look like right before the crash, okay? So again, the reason they look like this is because I'm telling you when we last flushed the cache, okay? I have to tell you that for this example to make sense. Otherwise, cell storage could look like any number of things. All right, so we have flushed the cache and then things crash. All right, so what happens? We're gonna recover, but in particular, so the machine comes back up. We're gonna walk through this. There's nothing in the cache. It's a cache. It is volatile. Nothing in the cache persists after a crash, right? The cache is wiped, right? Our challenge is to repair cell storage, right? We're gonna use this authoritative log to get cell storage to be what we want it to be. And you can see now it's wrong in two different ways, right? Both of these values for A and B are old, right? So let's see, this is the recovery process we had before, all right? The recovery process we had before is scanning backwards to the log, and it's looking to undo any uncommitted updates, right? So let's just see what happens. Let's see what happens, right? If we go through this, we're on that last entry in the log, remember, because again, we're scanning backwards, right? And we say, oh, okay, there's this update to T3. You know what, it's uncommitted, right? We're going to change the value of A to whatever the old value was, right? Now, this is a little bit of a weird usage of this code here, all right? Because, A wasn't 110. We didn't actually roll back from 110 to 80, but this gets us the previous value of A. in self storage. And, you know, that turns out to be what we want. Okay, but every other transaction here committed, right? Which means that nothing else is going to change about self storage, right? And before that was fine because self storage was basically keeping pace with the log, right? And now this isn't fine, right? We did have committed updates that didn't get into self storage. And this recovery process does not give us a way as is to get those commits back into self storage, right? But we can fix this, it's okay, right? We're just gonna add a second step to this recovery process, right? We're gonna undo in this phase any uncommitted updates that might have made it to self storage. And then we're gonna go through and redo updates that did commit. So effectively, we have to go through the log twice. To go backwards to remove uncommitted updates, and then forwards to commit updates, right? To commit committed updates, right? And I can imagine that, you know, in this scenario, this might seem like overkill, right? But remember that eventually we're moving towards a world where there's going to be multiple users, multiple transactions running in parallel, right? It is, for instance, not like in our example here, we're going to see like committed transaction, committed transaction, committed transaction, and then maybe an uncommitted transaction at the end. In a system that is dealing with multiple users, you could have uncommitted transactions sort of dispersed throughout the log, right? You could even have transactions in the log where there was no crash, but the transaction itself, you know, encountered a problem, maybe some invalid input or an invalid value or something like that in the code. And the transaction like explicitly sort of ended itself. So abort is the word that we often see for this. So there are good reasons to go through this entire process. All right, so we started out talking about performance, all right? But now, okay, you know, something has gotten worse, right? I've made the recovery process even worse, right? If this log gets really, really, really big, if it starts to grow without bound, it's not practical, right? This recovery process is impractical, right? So what we're gonna do is we're actually gonna end up truncating the log, which sounds surprising, right? It's surprising because like, are there parts of the log that can be discarded? This is supposed to be this authoritative resource. It seems really bad to get rid of parts of it, right? So like what parts, if any, could we discard? We have to know the outcome of every action that's a part of the log. And self storage has to reflect all of those log records, right? Again, remember, self storage is on disk. It's not on memory, right? We're thinking about self storage as, you know, although the log is authoritative, self storage is this kind of permanent data store, right? So the way that these systems truncate the logs, right? We don't have to worry about the details in O33. It's more important that you understand that this is possible. But what they do is they'll, okay, at the point when I'm going to truncate, flush all of my cached updates to self storage, right? Write a special kind of record, a checkpoint record, to sort of save our place in the log. And then we can truncate the log prior to the checkpoint record. It basically says, okay, at this point, self storage is consistent with the log, right? We can maybe not we could throw away the previous parts of the log or just store it somewhere else, right? And kind of archive it. Often logs are implemented just as a series of files. So doing that amounts to, you know, starting a new log file, deleting old log files, right? So again, the thing about this truncation to understand in the context of O33 is that it's possible. Okay, it is possible to keep these logs from going without bound. And, you know, that would be, it's a good thing. We hope that machines don't crash that much. Like we hope that this recovery function isn't called very often. If you have a really, really big log, and it means that your process of recovering and getting the machine back online is going to take so long. All right, so we do have some, we get some help from truncating the log there. So one other thing that is important at this stage, you know, this whole idea is, you know, it's built on the premise that these actions, right, these updates can be undone. and redone, right? I revert to old values of A, or I move forward to later committed values of A. But remember, these systems are real. There are some things that you can't undo, right? You can't undo dispensing cash from an ATM. You can't undo shipping a package, right? You can't undo shipping someone a llama, all right? This is a real concern in building these sorts of systems, and it requires like special care. So one approach for something like that is to wait for software that controls a particular action to commit and then take the action afterwards, but have some special way to detect like if an action has already happened and can't be redone, right? So you do have to think, you know, more holistically about like, what is my system doing as a whole? And that's, you know, that comes along with the idea of building a system and thinking like, well, what are the transactions here, right? How do we make these work, right? So now we have logging, right? So logging is this general technique for achieving atomicity. It is widely used in databases and in file systems. You can achieve pretty reasonable performance with logging, right? Writes tend to be fast, right? Even writing to that log, like I really want to stress, especially in contrast to shadow copies, writing to that log, appending a small piece of data to a log, it's a much, much, much faster operation than like copying over an entire file, right? We can make reads fast with cell storage. We can make writes and reads even faster if we add a cache, right? When we add those things, our recovery process does get more complicated, right? Because we want cell storage to reflect what's in the log. And when we're using a cache, we don't want to be constantly pushing to cell storage because then it's like, why are we using the cache, right? There are a couple of ideas here, key ideas. The idea of write ahead logging, so logging before installing, that's a key point here, right? Like the golden rule. And notice that, you know, here's a place where we start to see having this recovering process lets us clean things up, right? Once the machine comes back online. So at this stage, you know, we've done a pretty good job of achieving atomicity as long as we have just a single user, right? Logging performs better than shadow copies. There are systems that use shadow copies, you know, very kind of small, simple systems. Logging does add complexity, all right? But in most cases, we see logging. Right? Remember, we want atomicity. Like the reason we want this in the first place is it makes it easier for us to reason about failures, right? The action happened or it didn't, but it's not in some intermediate state, right? So what we're gonna start to deal with next week on Wednesday, Monday's a holiday, so on Wednesday, we're gonna start to deal with isolation, right? We're gonna go into this world where we might have multiple transactions running at the same time, but we want it to appear as if they were run sequentially, right? At a really high level, that means that the outcome of running these transactions in parallel, excuse me, is going to correspond to what would have happened if they were run sequentially, right? But of course, we are going to run them in parallel, right? We don't want the performance hit that is just running T1, T2, and T3, et cetera, right? So we're going to do that on Wednesday. And then we're going to have, you know, we're going to have transactions working basically on one machine. What we're going to do the week after that is spread things out over multiple machines. It introduces a network. You all know networks cause problems, but that is where we're headed. So we are essentially done with atomicity. We're going to move on to isolation. I hope you all have an excellent long weekend. I will stick around for questions. I and many of the TAs will be here for questions, but I will see you all in 1 week.